and share screen. Okay. So here's what we're going to talk about today. We're going to continue with convolutional neural networks. So we'll talk about different architectures. We've talked about the basic building block. Now, today we're going to talk about different architectures. How do we use them? And these architectures, you can typically just download them and use them to train on your data or on your project. Yeah. So we're going to talk about LeNet 5, AlexNet, BGGNet, FirstNet, Google LeNet, and then finally talk about data augmentation and transfer learning, something that is very common in computer vision. All right. So LeNet, this was, I mean, the first time it appeared was in 1998 by Lee Khan et al. It's one of the earliest convolutional neural networks, was used for optical character recognition. Yeah, you all know what is OCR. Basically, you look at a character and you try an image of a character and you try to automatically identify this character. So it's used to map scanned images of text to actual text. For example, we have this letter K, an image of letter K. The idea is to kind of try to automatically output the letter K, okay? So the architecture of the neural network, LeNet, was of this form. You had a convolutional layer, and we know what is a convolution now. It's just a filter that passes over the image, multiply weights by the value of the pixel, sum, and that gives you one activation, yeah, or one neuron, presents one neuron. And you pass this filter over the other pixels in the image, yeah, by doing some striding, and that gets you the next neuron, the next activation, and so on. So it's a one layer of convolution followed by pooling, was particularly average pooling rather than maximum pooling as we did last lecture. Then another layer of convolution, another layer of pooling, and then fully connected layers, two fully connected layers, and then a softmax. Who remember a softmax? Okay, softmax is the multi-class classification layer or neuron that is used for in neural networks, guys, for multi-class classification. That's what we refer to as softmax. Yeah, so here you would have, I guess, a softmax which has 26 neurons representing the 26 letters in the alphabet. Okay. Great. So basically, the input would be one image. It passes through these layers of convolutional pooling, and then a couple of fully connected layers, and then a softmax with 26 outputs. Right? Okay, good. Right. So the parameters of the the hyperparameters of the model was as follows: convolutional filters had a 5x5 with a 5x5 filter with a stride of 1. So we're doing a stride of 1, and the size of the filter was 5x5. You had an average pooling of size 2x2. So we're doing, you know, like a square of 4 pixels. And you're doing average pooling. So rather than doing maximum pooling, you're picking the maximum value out of these 4 pixels. You're doing average of the values of the pixels, and you're doing a stride of 2. You had 120 neurons for the first fully connected layer, and 84 for the second fully connected layer. Okay, and it was using TAN-H activation rather than ReLU. ReLU wasn't, I think, known back then. So was using the TAN-H, which what we used early in neural networks, in the first lecture of neural networks. Overall, you had a 60K parameters, yes, 60K different weights. If you compute remember that you're doing multiple filters or multiple convolutional kernels, and so you would end up with really different number of parameters here. Yeah? So the subsampling or the pooling did not involve any parameters, but the convolutions were multiple of them. And then you have the fully connected layers also have weights, and right, these two fully connected layers have weights, so you can do the math and get to 60,000 K parameters. So not a lot of parameters, it's reasonably small neural networks. Okay. So that was really the first, one of the first convolutional neural networks. So I'm just showing it for you for historical reasons. You will never be using Linet. And nobody uses Linet anymore. So AlexNet, that came in 2012. It's the winner of the ImageNet challenge. So ImageNet is a very important challenge in computer vision. It has basically 1,000 classes of different types of images, and the idea is to classify the image into one of these 1,000 classes. So you have images of cats and dogs, and ship and car and truck and so on. And the idea is to classify an object based on its image into one of these 1,000 classes. Yeah, and there is a challenge. You do a challenge yearly, and people participate in this challenge, and the one that gets the highest accuracy becomes the winner. So AlexNet was the winner of the 2012 challenge, ImageNet challenge. Yeah. So they were the first people to be able to train a really big CNN using GPUs. So one of the reasons deep learning is very successful these days is the utilization of GPUs. Yeah, it made training much faster, because before, right, it used to take forever. So why neural networks are out there since the 80s, but they became very successful lately just because you can now train them very fast using GPUs. Before, it used to be very slow to train them on CPUs. Yeah, so it takes a hell of a time to train them on CPUs, and people eventually gave up. So that's why they weren't very successful in the past. Okay, so what is the architecture of AlexNet? It looks like this. Yeah, you have a layer of convolution, then pooling, then normalization, something that is not really used anymore, but it was used in the AlexNet paper, so, or the AlexNet architecture. So just doing normalization over the features. Yeah, similar to what we did in the mini batch gradient descent, or in the batch gradient descent. Yeah, when we talked about normalization of features. Okay. And the pooling was maximum pooling, not average pooling like Linet. Okay, and then you have convolution again, pooling, and then normalization, and then convolution, convolution, convolution. So 3 layers of convolution, and then another maximum pooling, and then a fully connected layer, a fully connected layer, and then a softmax. 1,000 output, or 1,000 neurons in softmax, because you have 1,000. Yeah, so this is really how the network looks like. It's a complex network, deeper than Linet for sure, and much more parameters. And yes, it was really something that was very influential when it came out, because it was the first one to train a really big CNN using GPUs.
So based on what did he create this architecture?
Why or what?
No, based on what? Why did he do this architecture, like a convolution, then pool, then normalization?
They tried. So they tried different things. The idea was to try, these are hyperparameters. So they tried so many hyperparameters, and then at the end, this performed the best. Yeah, was doing convolutional pooling and then norm, convolutional pooling and norm. So there's really no principled reason for doing this. Yeah,
but like the parameters are very like large. There are many. We can add as much as we want layers.
Yeah, true. So they tried different configurations, right? And this seemed to do the best out of all of them. So there is no really principled reason behind this choice of convolution, the pooling, the norm, right? Why 3 convolutional after 2 layers of convolutional and pooling? Why 3 convolution? There is no really principled reason behind this. They just tried different settings. They didn't try everything, of course, but they tried different settings, and they presented the best architecture that they came up with. Yeah.
Okay, thank you.
You're welcome. Okay, let's look at one layer of AlexNet just to appreciate the number of parameters involved in it. So layer 1 of AlexNet has 96 11 by 11 filters applied at stride of 4. Yeah, so you have 11 by 11 filters, meaning that every one of these convolutions is just a map of 11 by 11 weights. Yeah, and they apply the filter at a stride of 4, so you move it 4 pixels to the left to get to the next portion of the image, and so on. And they applied 96 of these filters. Yeah, so they got the output should be size 96. Okay, so input was 227 by 227 by 3 image, so RGB image. What is the output size? Anybody can tell me from last lecture? Do you remember? And we have, right, 227 minus 11 over 4 plus 1. That gives you the width and the height. So it's 50, 55, I mean, by 55 by, what is that depth?
96.
What is that?
96.
96, exactly. Because I have 96 filters applied. Yeah, so remember the depth of the output is equal to the number of the filters. And the depth of the filter is 3. What's that?
No, I was saying filters.
Yeah, exactly. So 55 by 55 by 96. Okay, so that's the output of the first layer. What is the total number of parameters in this layer? Any thoughts? It's 11 by 11. So that's the number of parameters means the number of weights. It's 11 by 11 by 3 because the depth of the filter is equal to the depth of the input image. So it's 11 by 11 by 3 plus 1, which is the bias, times 96, because I have 96 of these filters. Each one would have different weights. So that's approximately 35K weights for the first layer alone. Okay, for the computations. The pooling, of course, doesn't involve any weights. So the first layer would have 35K weights or parameters to learn. All right? Okay. Layer 2 was pooling, maximum pooling using a 3 by 3 filter applied at stride of 2. Input from the previous layer is 55. So the input coming to the pooling is 55 by 55 by 96. What is the output size? Any thoughts? Pooling. When you're doing a stride of 2, so it's 55 minus 3 over 2 plus 1, that's 27. So you have 27 by 27 by 96. Yeah, exactly the same dips as length. Yes, 27 by 27 by 96, exactly. Okay, so that's the output size after the pooling. What is the total number of parameters in this layer? I've already answered this. For pooling, how many parameters are there?
0.
Exactly, 0. You don't have any parameters. It's doing maximum operation. So you have 0 parameters. Excellent. So the AlexNet full architecture looked like this. Yeah, you have the input was 227 by 227 because that's the size of the image, the input image, by 3 because it's an RGB image. We did 96 11 by 11 filters at stride of 4, padding of 0, then maximum pooling of size 3 by 3 at stride of 2, then normalization, then another convolution 256, 5 by 5 filters at stride of 1 and pad of 2, and so on. Okay. Finally, you have fully connected layers, which happen to have 4096 neurons, another one which is exactly the same, and then one fully connected layer, which is 1000 neurons. And then finally, you do a softmax on this. Okay. In total, it had 60 million parameters. So a lot of parameters. That's really what current convolutional neural networks, current neural networks are at. So you use really big networks with a lot of parameters. That's common in order for you to get good performance on your projects, particularly if you're doing computer vision. 60 million parameters in total. If you calculate the total number of parameters across all these layers, huge number. One of the interesting things about AlexNet was the first use of ReLU. So they're the one who introduced the rectified linear unit. They used norm layers, so similar to LeNet, but it's not common anymore. So nobody uses this normalization layer anymore. It used heavy data augmentation, and we're going to talk about this, what it means. Drop out of 0.5. So as a regularization technique, they use drop out. The batch size was 128. The algorithm or the optimizer was stochastic gradient descent with momentum. And they set the parameter, the beta parameter to 0.9. The learning rate was 10 to the power of -2, reduced by 10 manually when validation accuracy plateau. So they computed they drew the curve, the learning curve, and then once the validation accuracy plateaued, they kind of reduced the learning rate. So they update the learning rate and continued training the neural network. Yeah, they used weight decay, and they used something called ensemble of 7. So when in addition to just using one neural network, they used an ensemble of 7 convolutional neural networks. 7 different neural networks, AlexNet, trained, each with their own parameters, and then they combined the answers of these 7 neural networks, and that reduced the error from 18.2 to around 15.4. That's a very common technique. We're going to learn about this in ensemble learning or meta classification, and once we finish deep learning. So it's the next topic we're going to talk about, and it's a very successful technique. It's heavily used when you're doing production. So at the end, it makes a huge difference in production. So nobody cares about it in research much, but if you really want to win a competition, or if you want to build a model that performs really well, typically ensemble learning is a technique that helps a lot. The idea is to use multiple classifiers at the same time and combine the predictions from these classifiers. Yeah. Okay. VGGNet. This is again, so you can download AlexNet. So AlexNet is the code is there. Even the network is there. You can download it with its weights, and you can just use it on your project. We're going to talk about something called transfer learning at the end of the lecture, where I show you how you can use it with its pre-trained weights. You download a network like this and use it on your project. Yeah, provided that your project is somehow related to computer vision or image classification. Any questions? Okay, let's move on to VGGNet. It looks like this. So it came in 2014. But the idea was to use smaller filters. So AlexNet was using relatively large filters. So you had 11 by 11 as the first one. You had a stride of 4 and so on. And this one, you have smaller filters. So we're going to use smaller filters, but we're going to create a deeper network. Yeah. So AlexNet was the size, so it didn't have that many layers. VGG16 has 16 layers and VGG19 has 19 layers. So they're deeper as neural networks compared to AlexNet. Yeah. But in return, they use smaller filters compared to AlexNet. So what does smaller filter mean? It means that the number of parameters per filter is small. Yeah. But basically, they use only 3 by 3 filters with a stride of 1 and pad of 1. Yeah. And a maximum pooling of 2 by 2 with a stride of 2. And they didn't do any hyperparameter tuning on these. They just decided a priori we're going to fix it. So the size of the filter is 3 by 3. The stride is 1. The pad is 1. Maximum pooling 2 by 2 with a stride of 2. And they didn't worry about trying different hyperparameters there. Yeah? So changing the stride or changing the padding, changing the filter size. They said, okay, we're going to focus on creating just a deep neural network using some predefined or set filter sizes. Okay. So AlexNet had 8 layers, and then VGG16 had 16, and VGG19 had 19 layers. Okay, so it has fewer hyperparameters, of course, because you're fixing the filter size, you're fixing the stride, the padding, so it's really a matter of just learning the weights. Okay, so of course there are other hyperparameters like dropout rate, the momentum, the learning rate, and so on. These are hyperparameters that stay with us whatever neural network you're training. In total, it had 138 million parameters compared to AlexNet, which had 60 million. So it had more parameters overall because it's a deeper neural network. And was also a very successful, so it's a very successful neural network or CNN. So it's, again, the code is out there, the weights are out there, you can download it and use it in your projects. Okay, so it's I have a student who's currently working on a project related to computer vision, and we were just using VGGNet 19. So we downloaded it and just trained the final layers, these fully connected layers. It worked really perfectly for our project. Okay, ResNet. So this came in 2015. So what happens when we have a very deep convolution neural network? They run an experiment and observed the following, right? The curve on the left shows the training error, and on the right shows the test error. What do we observe from this curve? Anybody can tell me?
The more layers we have, the more the error.
Exactly.
If it was test.
So the one on the left is what?
The training error, and on the right, the test error.
It doesn't really generalize well.
So you said, you guys said two very good points. The first point is it has, right, the deeper the network or the more layers there are, the worse the error is, whether training or test. You can see this from the figure, both, right? For no matter what the number of iterations is, of course, the errors decrease as I train more and more. But overall, if I have a deeper network, so more layers, I tend to have a higher training error and a higher test error than 20 layers. But it's not generalization. So I don't agree with the last comment. It's not a generalization because if you notice, right, the difference between the training error and the test error is not so high. So if you compare the two red curves or the two blue curves, they're not, they're tracking each other. Yeah, there's the same trend, more or less. So as the training error decreases, the test error decreases, and they're not very far off from each other. The same thing for the blue curves. Yeah. So it's not a generalization error. It's just that the deeper model performs worse both in training and testing. Yeah. So it's not caused by overfitting. It's not that because the deeper layer has more weights and you have limited training data, or you have a certain fixed size of training data that you're overfitting. It's not overfitting because training error tracks the test error. What happens is it's a problem of exploding and vanishing gradients. Remember the exploding and vanishing gradients, where we said the more, right, the deeper the network is, by the time you pass the gradient from the output layer to the input layer, it vanishes or it explodes because you're multiplying it by weights and then passing it through nonlinearity and multiplying it by weights and passing it through nonlinearity. And so by the time it reaches the earlier layers, it already vanished. It's almost equal to 0. And so the first layers will not, the weights will not be updated, or they will be updated drastically. Yeah, so huge values, and that causes the error to increase. Okay. So it's an issue of exploding and vanishing gradient. That's very common in any deep neural network. Any deep neural networks, any neural network that is deep will always face exploding and vanishing gradient. Okay. But the intuition is the following. The deeper model should be able to perform at least as well as the shallower model. So basically, if it's a deep network, right, and I have a shallow model, at least the deep network could set the weights of these layers that are extra layers to 0, so that it mimics the shallow model. So intuitively, it should perform at least as well as the shallow model, if not better. Yeah, but because of the vanishing and exploding gradients, this is not the case. So what's gonna do in ResNet is the following. It's gonna copy the learned layers from the shallower model and setting the additional layers to identity mapping. What do I mean by this? They added something called the residual block. It's important to know this architecture, understand this architecture, so that if you wanna use it again in your projects later on, or you wanna download the code or the pre-trained model, you understand how to use it, yeah? So the idea is the following. You have a residual blocks inside the neural network. It looks like this. You have an input X coming from a previous layer. It goes through a convolution through a ReLU, nonlinearity, through another convolution, and then, you know, before another ReLU, you do the following. You take the input, not passed to these two layers, and you sum it with the output of passing the input to these two layers. So you have f of x plus x. So you're passing the input here through two layers and some nonlinearity that gives you f of x. You sum it with the identity, yeah, the input as is. Okay, and what does this allow the network to do? The network has the freedom of telling the weights in the residual block. So in this thing, if it sees that these are causing, right, some you know, worse performance, these weights, it will set them to 0. So it has the idea of bypassing these two layers completely. Yeah. So passing the input from this layer to this layer by setting the weights of these two convolutions or two filters to 0. Yeah. That allows me to pass these two layers. Yes.
How does it know which layers are causing this high error?
So it tries. So basically, based on validation error, tries to set these weights and then realizes that if it minimize the weights of these guys or set them to 0, this is better. If I pass the input from this layer to this, and that could change from one, you know, from one input to the other. Yeah. So then it eventually, it sets the weights based on validation error or trying different weights.
Okay. Thank you.
You're welcome. Okay, so this is how it looks like, the ResNet. It has the input, then 7x7 convolution, and then pooling, and then few 3x3 convolutions, additional 3x3 convolutions. You know, most of it is 3x3 convolutions, similar to AlexNet, to VGG, sorry, yeah? So it has mostly 3x3 convolutions. You just change the number of filters from some layer to the other. And then you have pooling, and then one fully connected layer, and then softmax. Again, 1000 here because I'm doing the ImageNet. So I have 1000 classes. So that's why that's 1000. Okay. Now, these are these ResNet connections. And these allow me to basically skip these two layers, pass the input as is, and then skip these two layers if I need to, and pass these two layers, and so on, right? And that changes from one input to the other. So based on the image that I'm given, sometimes it's better to, you know, pass the input as is. Sometimes it's better to convolute. Yeah, and that gives the network the freedom of mimicking some shallow neural network. What happens is when I'm passing the gradient, it can pass backward in these connections, yeah, without being multiplied by weights. And that avoids the problem of exploding and vanishing gradient because it passes through these connections, these identity connections, yeah. So there is a guarantee that some gradient will be passed all the way to the previous layer through these connections, through these residual connections, okay? Just understand the intuition behind it, yeah? You're not gonna implement it from scratch. Okay, good. All right, we're gonna do Google Lenet. Then we'll finish with data augmentation transfer learning. So I think we're gonna finish early today. Should I end here? Let's end here and start again. Was I recording or no? No.
Yes,
right?
it was recorded.
Yes, you are.
Okay, good. So then we'll talk in a second. Stop share. Stop record.